So, good morning students. Now we are going to discuss about the concept of direct execution. So, what is direct execution? In simple terms, we can say that direct execution is a concept of executing a process directly on the CPU without involving operating system. So, we will get a doubt that how without operating system how the CPU will execute a program. That we will see in detail in this session, but in this the objectives and what you are going to learn in this session is how to know what exactly the context switching happens in direct execution, and to get the idea of how direct execution differs from normal execution, and how to regain the control of CPU if it is directly executing on the CPU, and why system calls look procedure calls. Okay, now so the session description is here. In order to virtualize the CPU, the operating system needs somehow share the physical among many jobs running simultaneously. Right. See here, virtualization is nothing but if you are executing one process now and you need to give the chance to the second process also after some time. Okay. So, to effective the CPU, to use the CPU effectively without any interference, like see for example now we were executing process 1, so after some time you need to give chance to the process 2, right? So the basic idea is simple: run one process for a little while and then run another one, and so forth. By time sharing the CPU, in this manner virtualization is achieved. So now how virtualization is achieved is in between time sharing, right? So if the process 1 is executing 10 seconds for example, then it has to give chance to the process 2. Okay, and again process 2 has to execute another 20 seconds and then process 1 again. So with this time sharing concept, the virtualization will be implemented in operating systems. Okay, so this is about virtualization, but in this the direct execution, in the sense the program will be executed directly on the CPU. The program will be executed directly on the CPU without interference of OS. Okay, so now without interference, why I mentioned this term is actually when processor is executing any process, in between OS comes and it will switch to the second process. In between OS comes and it will switch to the third process again, right? So this is how the virtualization will be implemented, and the OS will be taking care of the virtualization concept here, right? So now, but in this limited direct execution, we have a problem that the process will be executed directly on the CPU without involvement of operating system, right? So but how this will be implemented, right? So in here we have a concept called limited direct execution. So what is limited direct execution means? So as I told you, the process will be executed directly on the CPU, right? So in order to build this virtualization concept, we have two issues, that is performance and control, right? So performance in the sense to moving from one process to another process 1 to process 2, we have to save the status of previous process and then only we can move to the process 2. See, for example, we have P1 and P2. If you want to execute the P2 process, you have to save the P1 process status first and then only you can move to the P2, right? So if you are continuously moving from one process to another process, then you have to save again and again the status of previous process, right? So here why the performance will be affected is, here the virtualization will not be implemented without adding excessive overhead to the system, right? And control. The second problem is control. Control, why I said is, as I told you earlier, the operating system will be there in between if it is normal execution, right? So once the process 1 executes, the operating system will interfere and then operating system will take control of it and then it will be assigned to process 2, right? So now I am saying that the process is directly executing on CPU, then it means that the operating system will not take control of it, right? So the process could simply run forever and take over the machine, right? So here there is a problem of control also, because it will take more time to execute and it will not give chance to the another one, right? So the direct execution is simply a concept of just run the program directly on the CPU, right? So now for that purpose only we have introduced the concept called limited direct execution. Okay, just we have added one more term called limited. It means that direct execution will be implemented with the limited basis. Limited basis, how this limited term will be implemented we will see now. Okay. Now see here how it is executing. Now operating system will create a process list and allocates memory for each and every program, and first then load the program into memory and set up the stack with arguments, that may be local arguments or global arguments, and after that clear the register and execute call main program. Once the main program call, it will be jump to the main and execute return from main, and then again free the process memory, whatever memory is allocated to that particular process, free that particular memory and remove the process list. And next, so now what is the problem of, actually what is exactly the problem implementing direct execution? As I told you, if the process should follow some ethical rules, like ethical rules in the sense, if any process is executing on the CPU, it should not access any other process information, right? So other process information in the sense, maybe other resources which is allocated to the other process, or any specialized or any personalized information which is only be allotted to second process, so that should not be accessed, right? So these ethical values should be followed by process. If that thing is not followed by the process, then it is a problem while we are executing the direct execution. Okay, so for that purpose only we have two modes here, user mode and kernel mode. For let us take for example, operating system is like OS will divide this like this, user mode and kernel mode. Okay, so when it is a program, when the program started for execution, the stack will be created to that process, and again heap memory and program control. So these are the some predefined registers, right? So when it is started for execution in the user mode, these stack and heap and PC registers will be created. When it is moving to the kernel mode, so the process when it is moving to the kernel mode, again the same stack, the same process stack information and heap information will be maintained in the kernel mode, right? So now user mode applications don't have full access to the hardware resources. In the kernel mode, the OS has access to the full resources of the mission, right? So when the process is there in the user mode, it should have limited resources access, right? When the process is moved from limited, user mode to kernel mode, then in this kernel mode the same process will have so many permissions to access all other resources, right? Fine. So now here we have seen something like system call, you can see on the board itself, system call. But why this is system call? As I told you, right? As I told you, if any process, if we are executing directly on the CPU, if we are executing directly on the CPU like process 1 and process 2, earlier we have mentioned that OS take in between response, like responsibility, and it will take care of the time sharing concept, right? It will divide the time in between and P1 and P2, and it will take care of moving from P1 to P2, P2 to P1 back again, right? But here, as we said, we are directly executing on the CPU, right? So in this case, the process itself have to move from one process to another process, right? The process itself have to move from one process to another process. So in this concept, we will implement the timer interrupt. Okay. generally we have a concept called yield, which will be implemented by this system call. Okay, so but in this yield, what it will happen, if a process is genuinely accessing the CPU, genuinely executing with this yield system call, after some time the process will be moved from P1 to P2. The process will be moved from P1 to P2. Like it is a trap instruction saying that it is a time to move from P1 to P2. P1 time is already over, we have to execute the P2. It will say that, right? So now here the system call, to execute a system call, a program must execute a special trap instruction. That is what I told you. Trap instruction in the sense, earlier if it is a genuine execution, we will use the concept called yield, right? So trap in the sense, we will forcibly, we will create one timer interrupt. We will create one timer interrupt. So with this system call, the process will move from one process to another. The execution will move from one process to another process, right? So this instruction jump into the kernel and raise the privilege level to the kernel mode. So when the process is executing in user mode, it will raise a system call, that is, we can say that trap instruction will be raised, and once the trap instruction is raised, then it will move to the kernel mode. The process will be moved to the kernel mode. In this kernel mode, the privileges of that particular process will be raised. So once in the kernel, the system can now perform whatever privileged operations are needed, like accessing the file system or accessing the resources, etc., and thus do the required work for the calling process. When finished, the OS calls a special return from trap instruction, which returns into the calling user program and reduce the privilege level, right? So when the process is executing in the user mode, as I told you earlier, it won't have special permissions or special privileged accesses, right? So when the process want to access the special privileges, like the process wants to access the resources or file system permissions, etc., then it will raise a trap instruction, and then the process will move from user to the kernel, right? So once the privileged instructions or privileged permissions are over and the work with the privileged thing or file systems, etc., is over, then again return from trap system call will be executed, and then it will move from the kernel to the user again. It will move back to the kernel to the user mode. When it is moving back from kernel mode to the user mode, all the privileges which is assigned to that particular process will be reverted again. That means it will be removed again. Okay. Now, how this limited direct execution will happen? So now see here, initialize the trap table. That means it will be initialized in user mode, right? So now remember address of system call handler that I told you now, from user mode to kernel mode. Here we will make some stack values and everything, right? Then it will execute. Next, see here, create entry for the process list and allocate memory again and load the program, set up user stack with arguments either global or local, and fill kernel stack with registers, and then restore registers from kernel stack and move to the user mode, jump to the main, and then return trap function, right? That means user to kernel and kernel to user. What I have explained earlier, it will be mentioned step by step here. Now see, save registers to the kernel stack and move to the kernel mode, jump to the trap handler. Okay. So handle trap, do work of system call and return from trap again, and then move to the user mode. So if trap occurred in user mode, we will handle the trap function, we will move to the kernel mode. Again work is done, again we will save the status in the kernel mode, and again we will get back to the user mode. That is what they have mentioned. Restore the registers from kernel stack and move to the user mode, jump to the PC after trap. Okay, PC in the sense program counter. Now once it is done, free the memory of process, remove the process from process list, right? Now, how the context switching will happen in this direct execution concept? Why? Because as we have already mentioned, if it is normal execution on the processor, one process is executing, the OS will take care of this context switching in between process 1 and process 2, right? Here process 1 and process 2, this context switching means moving from one process context to another process, right? So OS will take care of this context switching when it is a normal execution. But how this context switching will be implemented in this direct execution is, we have two different types of approaches to implement this context switching in direct execution. That is a cooperative approach and non-cooperative approach. Cooperative approach means waiting for the system call, right? And the non-cooperative approach is the OS takes control of it with a force, right? Yes, see, switching between process should be simple, right? The OS just decide to stop one process and start another. If a process is running on the CPU, this means the OS is not running, right? OS is not taking care of the control. Then there is a clearly no way for the OS to take an action. So if it is not running on the CPU, right? So then how OS can regain the control of the CPU when this direct execution is happening? That is what I have mentioned. We have two different approaches, cooperative and non-cooperative approaches. So in the cooperative approaches, waiting for the system call. As I mentioned earlier, so yield system call will be implemented. In this yield system call, the purpose of yield is used to periodically give up the CPU. Like we will have a timer interrupt in between. This timer interrupt may be 10 seconds or 5 seconds, right? So with this timer interrupt, we can implement the context switching. That means on the processor, process 1 is executing, we will give a time for 10 seconds to the process 1, and then obviously after 10 seconds is over, then obviously P2 will start automatically, right? So again P2 will execute 10 seconds and then again P1, right? So this yield purpose is to give a timer interrupt, right? Periodically give up the CPU. That means this much period, this 10 seconds period for P1. Once the 10 seconds period is over, then P2 will take over the execution, right? So for example, in this process, if any like P1 process have some infinite loop in the sense it won't see any timer interrupt and all, it will execute continuously. In that case, we have to reboot the mission. Thus, in that case, we have to reboot the mission. Along with this yield system call, yes, so with this yield system call, along with this yield system call, if the application also can transfer control to the OS when they do something illegal in the sense divide by 0, or if they want to access any file system which is not permitted to that particular process, or try to access the memory that should not be able to access, right? Because while creating the process itself, we will allocate some memory to that particular process, right? So while in the execution, in the direct execution, if this particular P1 process want to execute some other process memory, okay, which is not part of P1, then in that case also OS may take control of it, right? And this non-cooperative approach is the timer interrupt. So in this cooperative approach, yield system call is there. So with this yield system call, obviously the process will give a chance to the second one, right? So it is a cooperative approach. That means the process is cooperating to the CPU. And the second one is the timer interrupt. As I told you, 10 seconds or 5 seconds or 20 seconds in some milliseconds of time will be given to a particular process, and once the time is over, forcibly we will move from process 1 to process 1 to process 2, right? This is a timer interrupt, in between interrupting the execution of a process, saying that your execution time is over, okay? So the timer raise an interrupt every so many milliseconds, so many milliseconds in the sense either maybe 5 or 10, right? So when the interrupt is raised, the currently running process is halted, and save enough of the state of the program, and a pre-configured interrupt handler in the OS runs, right. So once the interrupt raised, the P1 status will be saved, and again P2 starts execution. P2 starts execution. Okay. So in this, the timer interrupt will gives OS the ability to run again the CPU, run again on a CPU. Okay. Yes, I told you when we are implementing this context switching, we have already known that if you are moving from one process to another process, we have to save the status of previous process, right. Either may be variables, either may be this current execution status of a process, etc., etc. Here scheduler makes a decision whether to continue running the current process or switch to a different one. If the decision is made to switch, the OS executes context switch. Context switch in the sense will save the previous process status and will move to the next one, right. Now here this context switching will be implemented through some registers. As I told you, few register values. This is general purpose register, PC, kernel stack pointer. It will stores the local variables, right, program counter, and these are general purpose register, and restore a few for the soon to be executing processes from its kernel stack, and switch to the kernel stack for the soon to be executing processes, right. So when we are moving from user mode to kernel mode, we have to store some registers in user mode, and then we will move to the kernel mode, and then kernel to user again in the same process. Now see here, initialize the trap table and remember the address of the previous one, and then system call handler, timer interrupt, right, and the start interrupt timer, start timer interrupt CPU in 5 seconds or 10 seconds. Here x milliseconds in the sense it may be 5 or 10 milliseconds, right. And then OS runs in kernel mode, timer interrupt, save the registers of A to K stack A and move to the kernel mode and jump to the trap handler. Since we are executing process A here, we are saving the process A register values. Now see here, handle the trap and call switch routine and save the registers of A to process stack A and restore the registers B from the process structure B and switch to the kernel stack B. Okay. So as I told you, A to B, here the process names are A to B, right, and from moving from A to B, it has to save all the registers, right, stack values, PC values, etc., etc., and then the status of A will be removed, right. So the execution status will be removed. So now we have to load the process B values also from the process structure B, process stack B, right. So then move to the user mode and jump to the B process PC, B process program counter, right, and then process B. Okay. Now, so this is about the limited direct execution. Here the limited direct execution, simply we can say that the operating system, without involvement of the operating system, the process will be executed directly on the CPU, right. So while directly executing on the CPU, the operating system may not have control over the process, right. So to get the control on it, we have used different types, right. So that is, one is system call approach and second one is timer approach. First one is a cooperative approach and the second one is non-cooperative approach. Cooperative approach in the sense we will implement a yield system call, right. Yield system call means after execution of some time, okay, the process will automatically give chance to the second one. The processor will automatically give chance to the second process, that is after some time, right. So it is a cooperative approach. That means the process, it will, like, processes are genuinely following the system call timer, right. And second one is non-cooperative approach. Non-cooperative approach in the sense we will use the concept called timer interrupt. Timer interrupt in the sense, so we will implement a timer interrupt, like 10 seconds or 5 seconds interrupt will be there. After this 10 seconds, process 1 will be stopped executing and process 2 will start executing. So before executing process 2, we have to store all the values of process 1. That is what? Save the registers of process A and into process structure A, right? So then we will store the process 2 values, that is restore the registers of B from process structure B. Okay, so that is what? Timer interrupt. In this way, this timer interrupt will be implemented in between two processes. Okay, so this is how the direct execution will be implemented. In this direct execution also, if any process wants to execute the memory which is not allocated to that particular process, or if any process wants to access the resources which is not allocated to that particular process, in this state the OS may take control of that particular process and it will take over the execution from the CPU, right? Yes. So now here the overall introduction. An operating system, as you know that it is an interface between user and the computer. It will always meant for handling the input and output and controlling peripheral devices. So these are the general activities that you can implement based on this concept. One real time which can indicate the direct execution concept clearly, and draw one scenario of context switching with direct execution and timer interrupt concept of direct execution. So that's all students. This you can assess yourself by following these questions, right? These are the self assessment questions and these are the terminal questions, and these are the reference books which is available for our operating system. Thank you.